Hello, I'm Hannane, and this is a joint work of Fahad, Panolan, and me. The title of the work is Partial Vertex Cover and Graphs of Bounded Degeneracy. So I will start the presentation with a short introduction about what the problem is, and then in the work we have two different results for PVC, and I will talk about those results, and at the end I will state some open questions related to our results. Okay, so you're probably familiar with minimum vertex cover problem, where we are trying to find the smallest subset of vertices which covers all edges of the graph. So our problem is partial vertex cover, in which we have a graph and an integer k, and we are trying to find a subset of vertices with size k, but we want to cover maximum possible edges. And we consider the problem for graphs of bounded degeneracy. We say a graph is degenerate if every subgraph of it has a vertex of degree at most d. And also like the minimum d that the graph is degenerate is the degeneracy of the graph. As you can see in the picture, graphs of bounded degeneracy includes many different sparse graph classes. So it's worth considering the problem on the bounded degeneracy graph. Okay, the first result is FPT algorithm. And the way I will describe the result is kind of different from the paper. I will try to be more intuitive. So we already had an FPT algorithm for graphs of bounded degeneracy. So our result is an improvement on previous results, but also it works for weighted graphs. And we present two algorithms for the problem with two different running times, as you can see them, with this and this runtime. Both algorithms use similar techniques, they just have a slight difference. The main technique we use is random separation. It's a variant of color coding. It's a well-known technique that it's used on graphs of bounded degree. We don't have a bound on degree in degenerate graphs, but we can kind of think that there is a one-sided bound on degrees in these graphs. The way we can say it is that we can consider an ordering on vertices of a degenerate graph in a way that each vertex has at most d neighbors among vertices comes after it. So like this is a vertex and it has at most d neighbors here, but it can have any number of vertices in this part. Okay, so the degree is kind of bounded from this side only. Okay. So how can we get this ordering? It's pretty easy. Considering the definition, we say the graph has a vertex with degree at most d. So we pick that vertex and we remove it from the graph. The remaining graph again has a vertex with degree at most d because it's a subgraph of the original graph. So we pick the vertex, we remove it from the graph, and we keep doing this procedure until all vertices are in the order. Okay, so again, we use a technique that is useful for designing algorithms on graphs of bounded degree, but we don't have a bound on degrees of a degenerate graph. But considering this ordering, we have a one-sided bound on degrees, and I call this ordering the posterior ordering. Okay, so in the algorithm, we give a degenerate graph G, and with edge weights, like the graph is weighted, and also we give an integer k. The algorithm is pretty simple. We consider a posterior ordering and vertices of G, and then we color each vertex of G with red or blue with probability 1/2 each and independently. And for each vertex V, we define a value. So this is the value we define for the vertex. And then at the end, we simply return the k most valuable red vertices. I will explain how good this algorithm would work. And also, this is the randomized version of the algorithm, and we eventually will de-randomize it. But first, let me explain what value of a vertex is exactly. Let's say this is V, and we have other vertices in the graph. Some vertices are red, and some vertices are blue. And so this is the ordering. And there are some edges incident to V. So there are some edges. Okay. So the value of V is the sum of all weights of these edges except edges going to a posterior red neighbor. Okay. So as we can see, the summation is over R neighbors of V, except someone which is red, so VR is the set of red vertices, and also it's a posterior neighbor of V. So we don't consider this edge and this edge in the summation because they are going to a posterior red neighbor. Okay. So this is what the value means. Here's a lemma that says the algorithm I just described would return the correct optimal solution with probability at least this much. First of all, this is a good probability because this means if we run the algorithm this many times, then we expect to find the correct optimal. And since this is a function of k, because d is a constant, then we're fine. Okay, so let's prove the lemma. The first thing that we need to prove is that for any set of red vertices, the sum of value of vertices of the set is at most the sum of weight of edges that the set covers. So for A that A covers, okay, so we need to prove this. Let me move into whiteboard. Okay, so we need to prove this. And for this, the first thing that we should notice is that if an edge is not covered by A, then the edge is not counted in the left side and it's not counted in the right side. So we only care about edges that A covers during the proof. Okay, so I consider some different cases. The first case is that we have an edge that one of its endpoint is blue. So the blue endpoint is not in A for sure because A is the set of red vertices. So this edge is counted in this side once and also in this side once in value of B. Okay. The other case is that we have two different two red endpoints, and both of them are a vertex of A. In this case, again, the edge is counted once here and also once here in value of U, because like the edge is not considered in value of V because U is a red posterior neighbor of V. Okay, so like I'm also considering the ordering on these two vertices. So we do not count the edge in value of V because U is the posterior red neighbor of V, but we do count the edge in value of U. Okay, then next one is that like V is not, let's say the one is not, U is not, and V is in A. Okay, so in this case, again, we count the edge in value of V. The edge is counted in value of V because we only ignore edges that are going to a posterior red neighbor, and U is not a posterior red neighbor here. Like U is coming before V. And also like U is not in A, so it's not counted in the summation. The last case is that U is in A and no, sorry. V is in A, U is not in A, but U is the posterior neighbor of V. So in this case, the edge is counted once in the right side, but it's not counted in the left side because U is the posterior red neighbor of V now, and we do not count this edge in value of V. Okay, so according to all these things, we proved that left side is less than or equal than right side. Back to this. Now let's consider a hypothetical solution. Like let's say subset S of vertices is a optimal solution for the problem. And also let's say S prime is the set of all vertices that are not in S, but they are a posterior neighbor for a vertex in S. We know that the size of S is K, so the size of S union S prime is KD. Like, because each vertex of S has at most the posterior neighbor, then each member of S would add at most the vertex into S prime. So the size of S prime is at most KD. Okay. Then with at least this probability, we will color all vertices in S with red and all vertices in S prime with blue. So we have vertices of S and we have vertices of S prime. Edges can be between two different vertices in S, but each vertex of S prime should be a posterior neighbor of at least one vertex of S. Okay. So with this probability, we color all vertices of S with red and all vertices of S prime with blue. And then we show that if this happens, then we have the value of all vertices of S is exactly equal to the sum of weight of edges S covers. So the proof is quite similar to what we just did. Let me get back to it. Okay. So The only difference is that in this case, so this is the case that make the inequality. So if we didn't have this case, then the equality would be a quality. So in this case, we have a red vertex, which is not in the set, but is a posterior neighbor of a vertex in the set. And we would not have this case when all vertices of S are red and all vertices of S prime are blue. Because this is a vertex which is a posterior neighbor of a vertex of S, and it's not in S itself, so it should be blue. Like this is a vertex of S prime, so it should be blue. So we do not have this case. And then the inequality would be equality, and so we're done. Okay. We prove both this and this, and considering this, we know that S is an optimal solution. So the sum of weight of edges that S covers is more than A. So like we have and by what we just proved, we have this is like the like S is the set with K most valuable vertices. Okay, but note that this only happens when all vertices of S are getting red and all vertices of S prime are getting blue. Okay, now we want to de-randomize our algorithm. For de-randomization, we use universal sets, and it's hard to explain the definition, so it's better if you pause the video and read the definition by yourself. And also, we have a lemma that we can construct universal sets of a good size in a good time complexity, so it's actually FPT with parameter L. And the only thing that we need to do is to like consider, so our main set is V, the set of vertices, and L is K plus KD, but it could be more than N, so minimum of N and K plus KD. And subset A is S union S prime, but because S union of S prime can have a size less than L, so we just consider a random superset of S union S prime. Only because we want A to be of size L. Okay. And then what we do is like we go through all sets in family F, and then we consider that this set is set of red vertices. And according to the definition of universal sets, there is a U that the intersection of U and A is S. Like the intersection contain all subset of A, so there is a U that the intersection of U and A is S union S prime, is S, which means that all vertices of S are red because they are in U, and U is the set of red vertices, and all vertices of S prime are blue. So exactly what we need. So we consider U as red vertices, and then we calculate the values as the same as before, and then we again return the k most valuable vertices. And the running time would be like just constructing the universal set and then doing a polynomial procedure for each set of the universal family, which will give us this running time. This is the first theorem. To get the other running time, we use lopsided universal sets instead of universal sets. And again, it's better if you pause the video and read the definition by yourself. And again, we have a lemma that says we can construct a lopsided universal set with a good size and in a good time complexity. We similarly set the parameters. So the main set here is again the set of vertices. P is K and A is S. The size of S is K. And Q is minimum of KD and N minus K. So it's KD, the size of S prime, but because and KD could be more than N minus K, so minimum of KD and N minus K. Yeah, just note that V should be a subset of V minus S, so the size of it can't be more than N minus K, and B is S prime itself, but because the size of it should be Q, so a superset of S prime. And again, we go through all sets in the family F and we consider the set as a set of red vertices. And because of the definition, there is a set that A or S is a subset of that set. So it means that all vertices or offsets are red, and the intersection of the set and S prime is empty set, so every vertices of B are blue, none of them are red. So this is exactly what we want. We want S to be red and S prime to be blue. So that's it. We just go through all set U in the family F and we calculate the value, and then we pick the K most valuable vertices at the end. We get the one which covers the maximum weight of edges. And the running time is again the constructing of the lopsided universal set and a polynomial procedure for each set in the family, which if we use this fact, since the running time here is a bit ugly, we will get this running time, which is the second theorem, and we are done with the first result. The second result is a polynomial compression for PVC. So for this part, we need some notations. First of all, we will allow self loops for our graph, but not parallel edges. And when we say the graph is degenerate, we mean it's degenerate without considering self loops. We show the set of neighbors of vertex V by NG of V, and we show the number of self loops on V with LG of V, and for neighbor and L for loop. And for any subset A of vertices, we show the number of edges that A covers with EG of A, and we use this for showing a complete bipartite graph. And probably we know what a polynomial compression is, but I put the definition here anyway, so you can pause and read it. But in case that you are familiar with polynomial kernelization, polynomial compression is the same. The only difference is that in the reduction algorithm, the input distance and output distance are from different problems. So in kernelization, input and output of the reduction algorithm are from the same problem, but here we will have different problems as input and output. So this is the main theorem of this part. It says given a D-degenerate graph G, which does not contain any K of P and P, a complete bipartite graph with partitions of size P, and also a number K, we can, in polynomial time, find a subset H of G with this many vertices, and H also has a weight on its vertices with these two properties. So the first property says for any subset of H vertices like S prime, the number of edges S prime covers in G is equal to number of edges S prime covers in H plus weight of vertices of S prime. The second property says that if we have a subset of size K in G covering at least T edges, then we have a subset S prime in H with size K, the number of edges it covers, plus the weight of its vertices is at least T. And the statement is a bit strange, especially because of this K of P and P, but because we wanted to get a better bound for planar graphs, we had to state a generalization somehow. So the theorem gives us two corollaries, and so what we had, let me write this here. So according to the theorem, using a polynomial time algorithm, we can output a subgraph H of G with this many vertices and that two properties. So the theorem gives us two corollaries. The first one is for planar graphs. Planar graphs are 5 degenerate, and also they are not contain any K of 3 and 3. So this would give us O of K3. We have the same thing for D-degenerate graphs. We can say like D-degenerate graphs don't contain K of D plus 1 and D plus 1. It's because if there's a subgraph of K of D plus 1 and D plus 1, then there is no vertex with degree at most D in it, so it's a contradiction with definition. Theorem will give us this instead. The second corollary for planar graph would give us O of K6, and it's worse than the first corollary, so the first corollary is kind of stronger. And also, this is resolving the open problem posed before, and there was no polynomial compression for planar graphs and also for degenerate graphs. So the idea of the compression is simple. We were just looking for a vertex V such that there is an optimal solution for PVC without V, and then we wanted to remove V from the graph and add some self loops to its neighbors. The idea is pretty simple, but finding a V like that wasn't very easy, so instead we looked for a structure. We call the structure nice structure, and we say a subset of vertices of size K plus 1 is nice if it's an independent set, and also for any two vertices in it, the intersection of neighbors of those two vertices is a fixed subset C. So this is how a nice structure looks. this is the subset of k plus 1 vertices, and for any two of them, the intersection of neighbors is exactly C, and they also have some private neighbors. And there is no edge between them, so it's an independent set. And why nice structure is good for us? Because we can easily remove the vertex with minimum number of incident edges, basically n of g plus l of g. It's because, like, let's say this is the vertex with minimum number of incident edges, then if there is an optimal solution for PVC containing this vertex, there should be another vertex that is not contained in the solution, and also all of its private neighbors. So this part. So in that case, we can replace like UK with U2, and it's better because the number of incident edges are more, and no private neighbor is already in the solution, so it will cover more edges. So from now on, we are trying to find a nice structure in the graph, and the question is that does a large degenerate graph contain a nice subset or not? So we are trying to compressing our graph. So as long as the graph is larger than a certain amount, then we have to be able to compress it. So we should find a nice structure in it, and we should remove the vertex with minimum incident edges. But the question is, do we have a nice structure in a large enough degenerate graph? For answering the question, we have two observations. The first one is that if we have a graph G and we have like two arbitrary numbers H and P, and we know that G contains a large enough independent set, so with this many vertices, and also vertices in the independent set has at most H neighbors, then we can say that the graph contains a nice subset or contains a K of P and P. And also, if we have the graph and we have the independent set, we can find the nice subset or the complete bipartite graph in polynomial time. The second observation is that any degenerate graph has an independent set large enough, and all vertices in that independent set has at most 2D neighbors. And also we can find that independent set in polynomial time of the size of graph. So now we prove the first lemma. The proof is with induction, and for each I between 0 and P, we prove that one of A or B is true. So there is a nice subset of I, or there is a subset of I, it's big enough, and also the intersection of neighbors of its all vertices has size at least I. And also this is like an intersection of all vertices in UI. This is not like a pairwise intersection as we had in theorem. Okay, so the base of the induction is easy. We just consider the whole I as U0. It is big enough, and also the intersection should have size at least 0, so we don't care. And let's say from a step I minus 1, we know one of A or B is true. If A is true, then we are done with step I as well. If B is true, then we have, let me draw a picture. So we have Ui minus 1 and Qi minus 1. And so the intersection of all neighbors of vertices here is Qi minus 1. So all of them are connected to Qi minus 1. And also we know this is at least I minus 1, and this is at least Okay, so we consider two cases. If there is a vertex like V outside Qi minus 1 and V is connected to at least this much vertices in Ui I minus 1, then we can say like the intersection of neighbors of V and Ui minus 1. So this part is Ui because it is big enough, and also the intersection of neighbors of its vertices is Qi minus 1 union V, which has the size I at least. And we're done. Otherwise, all vertices V outside Qi minus 1 have degree at most this much. And in this case, we say this is Ui minus 1. So in this case, we pick a vertex V in Ui minus 1, and then we remove all vertices, and this is like Qi minus 1. All vertices that has the common neighbor with V outside Qi minus 1. So Qi minus 1 is intersection of neighbors of all vertices, but they can have like pairwise common neighbors outside Qi minus 1. So we remove all vertices with common neighbors outside Qi minus 1. And we pick another vertex from Ui minus 1, and we keep doing it until there is no vertex to pick. I'm gonna say that we pick at least k plus 1 vertices, and basically we found a nice subset because vertices that we picked, the pairwise intersection of their neighbors is Qi minus 1 because we remove all vertices that we don't like them. In one step, note that V has at most H neighbors. So this here we have H vertices at most, and any of them is connected to this many vertices at most. So we say like in one step, we pick this many vertices, and the size of Ui minus 1 was like so this is more than k, and so it's at least k plus 1. So we pick at least k plus 1 vertices from Ui minus 1, and those are the nice subset that we were looking for. We are done with the induction, and at the end for P, we know one of A or B is true. If A is true, then okay, there is a nice set in the graph. And if B is true, then we have like UP of size at least P, and everyone is connected to at least P vertices. So G contains a complete bipartite graph. So we are done with the proof and the next one. So for proof of the next lemma, first we show that a D-degenerate graph has many vertices with degree less than 2D. We just say like, let's say T is number of vertices with degree more than 2T, then T multiplied by 2T plus 1 is at most the sum of all degrees of the graph, and it's at most 2ND. Like the D-degenerate graph has at most ND edges. So we solve this and we get this. Okay. So G has at least this many vertices with degree at most 2D. And then there is a D+1 coloring for G's. I mean, we can color vertices of G with D+1 colors such that two endpoints of every edges have different colors. And why do we have a D+1 coloring? So we said that we have a D posterior ordering for G. So every vertex is connected to at most D vertices after it. I start from here, and we have D+1 colors. So just color the vertex with a color that doesn't appear in its posterior neighbors. So it has at most D posterior neighbors, and there should be at least one color that we didn't use. So we can color the vertex with that color. And then we go for the vertex before it, and so on. So we color all vertices. So there is a D+1 coloring for the degenerate graph. So if we consider all vertices with degree at most 2D, so we have this much of them, so we can find this many vertices among them with the same color. And when they have the same color, it means they are an independent set. So we found an independent set with this size. We can find it in polynomial time. As I said, we just consider the coloring, and we consider all vertices less than 2D, and that's it. Okay, so we are done with the proof. So now we know that in the degenerate graph, we have like a large enough independent set that all vertices in it has degree at most 2D. And also we have the first lemma saying that if we have a large independent set and degrees are small, we can find a subset, or there is a complete bipartite graph. So we say that as long as we have more than these many vertices in the graph, we find an independent set I of size n over D+1 to D+1, which is this. So this big independent set, this would be H in the first lemma. And all vertices in the independent set has degree at most 2D. We use the first lemma now, and we know that our graph doesn't contain any k of p and p. So we can find a nice subset in it. And then from the nice subset, we remove the vertex with minimum number of incident edges. And after removing it, we add necessary self loops to other vertices, and we keep doing it as long as n is more than this amount. Okay, so we almost proved the theorem. We're just like have a weight function on vertices here, but we were working with self loops. Note that the number of self loops on each vertex is at most n. It's because we only add self loops when we remove an edge. It's even strictly less than n. So we can encode number of self loops with log of n bits. Also from the first part, we have an algorithm with this running time for finding PVC. Okay, so we consider two cases. If log of n is less than, and if it is, okay, so if log of n is greater than dk, then these algorithms would run in polynomial time, and it will like act like a compression. And if log of n is less than dk, then we can encode the weights using dk bits. We are done with the theorem. Now we can ask some similar questions. The first one is that can we get the similar results on bi-click free graphs, which is a superclass of bounded degeneracy graphs. We say a family of graphs is bi-click free if there is a P where no graphs in the family contains K of P and P. And the second question is that, so we have linear kernel for dominating set in some class of graphs like planar graphs and H minor free graphs. And dominating set is kind of similar to PVC, and the question is that can we get a linear kernel or compression for PVC and planar graphs. Yeah, that's it. And thank you.